Hi guys, so today we're going to talk about a different way heat can be transferred, and that will be radiation. So we talked about conduction, we talked about convection, and now we're going to talk about radiation. So for example, here you have fire. The fire will emit light. So this light here is actually electromagnetic waves, and electromagnetic waves carry energy which is called radiant energy. So that's a way for heat to be transferred from one place to another. So radiation here, in that case, does not need the medium. Okay, it can be transferred through space, empty space. Whereas conduction, of course, you need the medium, and convection, of course, you also need the medium. Okay, so we're going to talk about radiant energy, which is the energy of electromagnetic waves. So, for example, when you are exposed to the sunlight, you see that you know that UV can burn, can cause burn. So that means UV is carrying energy. Okay, so energy is carried by electromagnetic waves. So here you have different examples. So a fire, when you feel the warmth, that will be infrared. Infrared are like heat wave. You can have light waves. If the temperature reaches like 1,000 Kelvin, you're going to have visible light. You can have radio waves. So longer the wavelength is, smaller the energy is. Okay, so that means the energy here, the radiant energy is proportional to the frequency. So if you have long wavelength, it's going to carry less energy than short wavelength. Okay, so visible light will carry more energy than infrared, and infrared will carry more energy than radio waves, for example. So a nice example comes, I have a nice simulation here. You see in a microwave, the way the food is heated is through radiation, through microwave, right? Microwaves are electromagnetic waves, a few centimeters long. And what's happening here, we're going to have an electric field and a magnetic field, but it's the electric field that will shake the molecules. It will make them go faster, so it will increase the kinetic energy. So the energy from the electromagnetic wave is transferred to the molecule. So it means it's also a way for heat to flow, right? And for energy to go from radiant energy here to thermal energy of the molecules, being water molecules. Okay? Go to slide 20. Oh, okay. So it's about the human body. So human body has different ways to get rid of the heat. The best way will be convection. Okay. It's like forced convection. So it means because of the heart. Okay. The blood is gonna transfer the heat out through the blood vessels, and then it will the blood which is cooling down will cool down the rest of the body. So that's the most efficient way to cool down. A different way is through uh, conduction, but that will be a very small way. But you also have radiation. Okay, so it means we are radiating here in the infrared, and by emitting infrared here, electromagnetic wave, we can cool down. We have also sweating because water, when it's going to turn into vapor, it's going to take away the energy from the body. So we have different ways to regulate our temperature. So radiation happens when it's electromagnetic waves that will transfer the energy. So it's called radiant energy. So that's the way heat can be transferred, okay, can flow. Now, you see here you have two cases. So you have a black box and a white box. And of course, in this case, the temperature will rise very quickly. Here it will take more time. But once it's in thermal equilibrium, they will have the same temperature as the outside. So we say it's a thermal equilibrium. But in that case here, you see that it will absorb most of the radiation. Okay. So we say it's a good absorber and it will reflect, but very, very little. At the same time, if it's in thermal equilibrium, it will emit exactly the same amount of radiation it is absorbing, okay, because it's in thermal equilibrium. The sun is not in thermal equilibrium because, of course, it's fusing hydrogen into helium. But in that case, you see, you have a good absorber is also a good emitter. In that case, okay, so this is a white box. What's going to happen? It's also it's going to be hit by this electromagnetic wave, but it will reflect most of it, right? Maybe it will absorb some of it, okay, but very little. 80%, 90% will be reflected. So in that case, we say it's a poor absorber and a poor emitter. Good absorber means good emitter. So we're going to call that a black body. So it's an important concept in physics. Okay, so what's a black body? So it's an object like this black box, for example, could be the human body also, can be thought as a black body. The sun can be thought as a black body, or the earth, right? So it means that all the radiation is absorbed and the radiation that is emitted only depends on the temperature. So the amount, the total amount, how fast the power emitted, okay? So the energy emitted per unit second will only depend on the temperature, and also the peak wavelength, so it means the color will also depend only on the temperature. So this is what we call a black body. Okay, so I will explain more, but that will be the definition. So here, that comes from the book Paul Hewitt, Conceptual Physics, which is a very good book. So you have this box here, that will be also a black body, even though it's white inside. You see, when you look through the hole, you see a black hole here. You don't see the white. And this is because all the radiation coming from the sun or the light outside will be totally absorbed. Because since it's white inside, it will be reflected, eventually it will be absorbed, but nothing can escape. Okay, so it's a good absorber. Now, you might think that no radiation is coming out. It is coming out in the form of infrared. And that infrared, if you look at its peak wavelength, it's going to give you the temperature of the inside. This is also here, it's behaving like a black body because all the light hitting this pupil will be absorbed. Okay, so that will be a black body. So that will take us to Max Planck law of black body, okay, or the Max Planck radiation law that says when you have a perfect black body, like almost the sun, the peak wavelength, okay, the peak wavelength will be inversely proportional to the temperature of the body. So the photosphere here the temperature is about 6,000 K, and the peak wavelength is green. In addition to that, the total amount of radiant energy, so the total amount of energy emitted per unit second, okay, is also temperature dependent. So we're going to see it depends on the temperature to the fourth power. So you see, Max Planck derived this curve. So he found the equation for this curve here. Okay. And if you look at the peak here, you're going to get the peak wavelength, and that will give you the temperature. And if you look at the area underneath the curve here, you're going to find the total amount of energy emitted per second. Okay, so that's called the Max Planck's law of radiation, or Max Planck's law of Blackbody. So I'm going to show you a simulation, but here you have the Earth. You see the peak wavelength is going to be much smaller. Okay, much smaller. This is a logarithmic scale. So the wavelength will be in the infrared. Using that wavelength, we can find the temperature. Of course, it's much smaller. That means it will be infrared. So the Earth is emitting infrared, and the amount of energy emitted by the Earth, it's much, much smaller. I have a picture here, so that will be, you see, the sun, the peak wavelength is green. So you find that using Green's law, and the total energy emitted per unit second, okay, will be this area underneath the curve. And we're going to see it depends on the temperature to the fourth power. And you see the Earth here. So that's what Max Planck was able to derive, okay, in the early 20th century. You see the Earth here doesn't emit much radiation, not a lot of energy, and the peak wavelength is in the infrared. Okay, so you can see the temperature. Okay, the wavelength, the peak wavelength, depends on the temperature. It's an inverse law. So you multiply the temperature by 2, the frequency will be divided by 2. And of course, you're going to get less radiation being emitted per unit second. So let's look at a simulation, if I can find a simulation here. Okay. So what you see here, you have the power, okay, emitted per unit second, per unit area, and for a given wavelength. Okay, so you have the intensity for a given wavelength. So that's going to be the sun. And you see that the sun will emit the most of its energy in the green. Okay, so the green photons will be the largest photons emitted. So a lot of green photons. Okay, so the peak wavelength is the green, in the green. And what you see here is that by looking at this peak wavelength, we can find the temperature of the sun. And if you find this area here, we can find the total amount of energy emitted per unit second. Okay, so it depends on the metabolism, quote unquote, of the star. So how fast it's burning its fuel. Now, if you take Sirius here, so Sirius has a temperature multiplied by 2, about, relative to the sun. So here we have a white star, even though it's the peak wavelength is green. You are mixing all the colors, so you're gonna get white. Now, if you take Sirius here, which is a blue star, it's the brightest star that we can see. Now, how to make it smaller this way. You see that the peak wavelength, it's going to be in the blue. Okay, so it's a blue star, but you also see that it's emitting much more energy per unit second, so it's losing a lot of energy per unit second, so it means it's burning its fuel quicker, so it will die also sooner, right? So if you multiply the temperature by 2, okay, the amount of energy emitted per second will be multiplied by 2 times 2 times 2 times 2. So 16 times. So the amount of energy is larger. Okay, so if you take something with a lower temperature, like a light bulb, now it's going to peak in maybe infrared. So you're going to see some red, but maybe it's going to peak in the infrared here. That will be the temperature that you can find using the peak wavelength. And you see that the amount of energy being emitted per second, it's lower. So it has a lower metabolism, if you want to think about that. If you look at the Earth, it's even smaller, right? It's still infrared, but the wavelength will be larger. Okay, so this is the Blackbody law. Okay, it has like a bell shape. So let's go back to the slide. Okay, you see that the sun is like a light bulb, but a 4 times 10 to the 26 watt light bulb. So joules per second. So that will be the total amount of energy emitted per second. So if you find this area under the curve, then you will find that this is going to be the power emitted, and it will be proportional to the temperature to the fourth power. So from this, you can find this law. So this is called the Stefan-Boltzmann law of radiation. And it says, let me write it for you. If you have a perfect emitter, okay, perfect emitter, perfect absorber, a perfect black body, so then you have that the rate at which energy is being emitted, okay, so that will be the oomph of the black body. It's going to be proportional to, so here you have a constant. This is called the Boltzmann constant, be proportional to the area. Okay, so that makes sense because, of course, if you have a large area, you're gonna emit more, you're gonna lose more heat. Okay, whereas if you have for the same temperature, smaller area will be less heat can escape, and proportional to the temperature to the fourth power. So that will be Q over T will be in watts. So that's going to be joules per second. Area is in meter square, and temperature will be in Kelvin. Okay? Now, that will be a perfect black body, but if it's not perfect, then you need to add another constant here, E, and E will be between 0 and 1. So E equals to 1. That means that it's a perfect black body. Okay. So for example, if you have again a black box and everything that the box is absorbing will be emitted to the environment. Okay. So it's in thermal equilibrium, then E equals 1. If you have a white box, okay, so that means radiation here is totally reflected, so nothing is absorbed, okay, so then E equals 0. Usually it's in between, but stars, you can say E equals 1. Now the constant, so there is a constant here, and that will be the Boltzmann constant. Okay? So here you have the term that we use. That will be the Boltzmann constant. That will be the power emitted by a surface at a temperature T. Okay? So it's used a lot in astronomy because it means, let's say you have two stars. You have a 6,000 Kelvin star like our sun, so it's a white star. And you have the 3000 K star, so that will be a red star, so it's not as hot. So the peak wavelength here, it's going to be red, sorry. The peak wavelength is going to be green, maybe like our sun. You see the ratio for the temperature is 2, but the amount of energy, okay? So if you multiply the temperature by 2, the amount of energy lost per unit second by this star will be multiplied by 16. So if a star is twice as hot, it's going to emit 60 times more power. So it means that it will run out of its fuel quicker. Okay, so it will have a shorter life. So it means die. What it says, live hard and die young. Okay, so that's the idea. That will be for the same area. Now you can have a cool star like Betelgeuse, which is red. It can outpower a hot star like a blue star like Rigel if the area is large enough. Okay, so even though you have even though you have a cool star, but if the area is very, 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 very large, then you can still emit a lot of power. So it's very interesting. So here they talk about Betelgeuse. So Betelgeuse is one of the stars of the Orion constellation. So Orion is a hunter, was a hunter, I guess. So this is Orion here, what it looks in the sky. And he has a bow. You can look it up online. And on his shoulder, he has a red star here. So that's going to be Betelgeuse. So Betelgeuse is a red giant. Okay. It has run out of its hydrogen already. So it's got very big. And then it's supposed to go supernova at some point, but we are not sure when it's going to happen, right? So anyway, you see that it's so big that if you place Betelgeuse here, and you see the sun is very tiny there, Betelgeuse will go even beyond the Jupiter orbit. So it's really, really, really big. Okay. And it's very cool. And even though it's very cool, you see, it's emitting more power than the sun because it's very big. So the sun is at 6,000 K, so twice the temperature. Okay, so if the sun and Betelgeuse were the same size, the sun will emit 60 times more energy per second, right? But not the case here. Okay, so Betelgeuse is emitting more than the sun because the sun is 10 to the 26. So there is a ratio of 10,000. So the sun is emitting less than Betelgeuse because Betelgeuse is so big. Okay, so let's do this problem. It comes from your book again. You see, for the sun, the temperature is about 6,000 Kelvin. And the power, okay, so the amount of energy per unit second emitted by the sun is about 4 times 10 to the 26 watt. So it's 10,000 less than Betelgeuse, even though Betelgeuse is 3000 K. So that's because the amount of energy per unit second, okay, so the power is not only proportional to the temperature to the fourth power, but also proportional to the area. Okay, so they want you to find the radius. And the area of a sphere is about 4 pi r square. Okay, so you just plug it in. So power is 4 times 10 to the 30. And then you have Boltzmann, what's the constant? 5.6. So it's going to be 5.6 times 10 to the negative 8. So we suppose that E equals 1. Okay, the area 4 pi r square. And then you have the temperature to the fourth power. And you are solving for R. So you can do it step by step, maybe. Okay, so to be on the safe side, what you can do, you can just put your area here and you can solve for the area. Okay, so you can do that. So that will be the power. So it's going to be 4 times 10 to the 30. Okay, you divide by that number. So 5.6 times 10 to the negative 8. Enter. And then you divide by 2900 raised to the fourth power, which is 10 to the 24, yes. So the area is 10 to the 24 meter square. These are numbers so big that we cannot comprehend how big it is. Just by comparing the sun and Betelgeuse, then you can have an idea. So then you divide by 4 pi. So you divide by 4 pi. 4 pi. I can't see anything. I don't see where pi is right now. Pi is here, so 4 pi. Okay, and you take the square root, which is about 3. So the radius is about 3 times 10 to the 11 meters. Okay, so then you can convert that to kilometers and try to find out. Otherwise, it's too hard to understand. You can compare that to the orbit of Jupiter, and then it kind of makes sense. Okay, so this is how you use that Boltzmann law. So you see, the best way to write this law is using Q over T. So the amount of energy per unit second. So that will be the radiant power, right? So that's going to be proportional to the area and to the temperature to the fourth power, if it's a perfect black body. So again, what's a black body? It's a body then whose with the amount of radiation emitted, okay, depends only. So the energy per unit second will depend only on the temperature. And the color or the peak wavelength also depends only on the temperature. So that's the definition of a black body. Okay, so black body and thermal equilibrium. So if you have like a so if you have a body which is in thermal equilibrium, that means that the amount of energy that it absorbs will be equals to the amount of energy that will it will emit, right? So that will be a perfect black body. But you can have a black body that will absorb more than it emits and still be a black body. So for example, here, here is an example. So a black body does not have to be in thermal equilibrium. So you have a pizza. So let's say the pizza is a black body. You see that it's going to emit in that case. So it's a very hot pizza and it's very cold outside. Obviously, it's going to emit more than it absorbs. So in that case, it's a net emitter. Regardless, we can still find, the peak wavelength here. So that's going to be infrared. So it's emitting heat wave, of course. And then you can find the temperature of the pizza. So in that case, before it's being totally cooked and very hot, you place it in the oven and now it's a net absorber, right? So when a black body is not in a thermal equilibrium, so it means it does not have the same temperature as its surrounding. So then you can find the net power, right? So you take the power absorbed minus the power emitted. So this is what in your textbook, they have this example here, which is a nice example. So you can pause the video. Let's say you have a oven. Actually, it's not an oven. It's a stove. Okay. Temperature is 18 degrees Celsius and it's not, on. I mean, there is no wood. So, and the temperature of the room is 18 degrees Celsius. So in that case, so you have your stove. The image, the picture I have put is not great, but you get the idea. So you have your stove here, okay? And it's 18 degrees Celsius and the outside is 18 degrees Celsius. So what's going to happen? Okay, all the energy absorbed by the stove, okay, so the radiant energy that comes from the room will be absorbed, okay, almost like E is, forgot what E is, 0.9, so 90%, okay, will be absorbed, the radiation that hit that stove, and 90% will be also emitted. Okay, so it means everything absorbed will be everything emitted. So if they ask you to find the net radiant power, so in that case, it's going to be 0, right? Because whatever is absorbed will be whatever is emitted. So it's in thermal equilibrium. So if more is absorbed, so then it's going to increase its temperature. If more is emitted, the temperature will decrease. Okay? So this is the case in the second example here. So now the stove is at 198 degrees Celsius and the room is 29 degrees Celsius. Okay? So find the net radiant power generated by the stove. Okay? So it's emitting energy, but it's also absorbing energy. So you need to find the net power. You can use this equation. So you can stop the video and it's not that hard. So that comes from your book, again, Johnson and Cutnell. In a new edition, it was not there in the older edition that I have. Okay, so the area of your black body, of your stove is 3.5 meters squared. So it's not in thermal equilibrium. E equals 0.9, so it's not a perfect black body, but close enough. The temperature inside the black body is 471 K, and the temperature out is 302 K. So that black body, okay, so it's gonna emit energy out to the environment. Okay, so at the rate of Q over T, but that will be out. And it's also absorbing energy from the environment, right? So that will be Q over T in. But for both of them, you can use the equation Q over T is that 0.9 times the area times T to the fourth. Okay? So you can try to do it. So Q over T out. So how much is being emitted? Okay, so that will be out. That's gonna be so 0.9 times the area 3.5 times the temperature. So out depends on the temperature of the black body, which is 471. So 471 to the fourth power. So I should not have put in and out here. It's kind of confusing. So let me put the temperature here so you can see. So that will be 471 K, and outside is 302 K. Okay, so this is the emission. Okay, it's producing energy per unit second, and that will be for this equation there. And then you have it's absorbing energy in from the environment. So it's going to be 0.9 times 3.5 times 302 to the fourth power. Okay, now we can see that the net power will be out minus in, so it's gonna be 0.9 times 3.5. You can factor out, so it's gonna be 471 to the fourth power minus 302 to the fourth power. And the unit will be in watt. So you can try to do that. So 471 raised to the fourth power, okay, minus, and then you have 302 to the fourth power, okay. You take 90% of that, okay, and you multiply by the 5. Okay, and I forgot to multiply by Boltzmann coefficient, which is 5.67 times 10 to the negative 8. Okay, so you have your sigma here, the Boltzmann constant. Otherwise, it will have given me such a big number. So times 5.67 times 10. You will be in big trouble if you have that much of energy in a room. So 5.67 times 10 to the negative 8. Yes. And you get about about 7,000 watts. Okay, joules per second. Okay, so let's see. Oh, you can look at your book, and it's a solved problem. So they take you step by step. Like so many steps sometimes can be confusing, but at the end you get the same answer, about 7,000 watts. So let's go back to the sun. If you take the example of the sun, it's not in thermal equilibrium with the environment, because inside the core, okay, the energy is being produced. Okay, so it's fusing hydrogen into helium. So it's, of course, it's going to be a net emitter, but nevertheless, it's still a black body. Likewise, the human body, okay, it's also, you have some metabolism, you're going to burn fuel, and of course, you're going to emit energy. So, of course, you are not in thermal energy because your body here is at 37 degrees Celsius. So, if it's cooler outside, okay, you're going to emit energy here, but it still can be considered as a black body, even though energy in is not equals to energy out. Okay, so here are some applications. So if you have a satellite, so in that case, this is, I think it's Hubble telescope, but in orbit around the Earth. So if you have a satellite orbit around the Earth, you don't want to have a black body. So if you are on the sun side, you want to make sure that body here will reflect sunlight, because you want to protect the electronics. So it will be a pore absorber. So it's not a black body, so you cannot use Stefan-Boltzmann Stefan law. And when it's in the dark side, okay, when it gets to the dark side, then it will prevent the heat inside from leaving, right? So it's a pore absorber and pore emitter, because you want to protect all the electronics inside. And then there was these cute examples in your book. So you have two kinds of lemur. So this one is a white lemur, and it's okay. It lives during the day, so it's active during the day because it's a pore absorber. So it means even though it's very hot outside, because it's white, it will reflect most of the light. But some places here it has dark area on its skin, so it can still absorb some light. Okay, and during the night it's a pore emitter. This one is dark and it's only active during the night. Okay, so that's why their color are not the same. So another example that I have found in the older edition of your book is a water solar collector. So it uses the energy from the sun to heat up a house, for example. So it's gonna heat up water here, and the water, you have a heat exchanger here. So the water that is hot here will heat up the domestic water there. So the point is that you have this device here, and you see those tubes are dark. So they are coated with dark paint. So that way they will absorb the maximum radiation from the sun. Okay. So it's like a black body. In addition to that, the tube also is made of copper. Copper is a good conductor, Okay, so it will transfer heat to the water very quick because it's a good thermal conductor, so the heat will be able to transfer very quickly. So they use copper, and that will be for conduction. So the sunlight, okay, energy from the sun is absorbed through radiation. In addition to that, they put a glass here, so you have a piece of glass, so you avoid convection. Okay, you don't want to have air, and you don't want the air to take away the heat absorbed by those tubes here. So you are using concept of convection, conduction, radiation. Three ways heat can be transferred. So here you have the energy from the sun being absorbed by this system of tubing here. You have a coil. Okay. What else? They give you this example also. So here you have an air pocket here to avoid convection. Okay, so not to lose part of, or if it's cool, you want to keep it cool. But inside here you have aluminum foil, or you have something like silver surfaces to reflect the heat. So it's keeping warm, right? So you don't want the radiation to escape. Okay, so you don't want a black body, you want something that will be a poor absorber of heat. Okay, and then you add some insulation there. And the air in between here will be a bad conductor. So there will be very little conduction. So you can look at your book here. You have if you go down here, you have these examples there. You have the Hubble telescope, and you have a thermos bottle there. Okay, so that will finish the unit. And next time we'll talk about, so here you have a nice summary. We'll talk about change of phases, and that will be it. I will save the thermodynamics introduction for another time.